The suits!
Hey, all right, we are good to go. Welcome back to the second of our closer to real engineering. I guess we get to call this like fundamentals of different kinds of engineering. We'll probably come up with more specialized names at some point. Today we're going to be talking about, before we dive into like, I think the first specific, what do we call it, topic area in engineering that we discussed last week. We're talking about bodies of knowledge and knowledge graphs. Would probably be units, looking at keys, ideas, and units and dimensional analysis, ways we can manipulate and understand units and how to handle them in difficult problems. But for today, there's one sort of overarching set of concepts that I'd like to talk about with respect to systems engineering in particular. So we're going to talk about four key models in systems engineering that help us understand a lot more of the overall engineering process in general. I don't know if that's legible back there. I'm trying to say a little bit new, but these end up having a lot of different and interesting relationships to all sorts of different and interesting kinds of problems and problem-solving techniques. We're going to talk about them largely in sort of a qualitative sense. I'm trying to calibrate this course as sort of like a maybe second or third semester engineering survey level of undergrad difficulty, or at least topic, just sort of broad engineering basic concepts, right? Get a survey for the field. So let's assume there's some degree of, I don't know, modest calculus knowledge here, but we're not going to get too quantitative with it. So without any further ado, the first key model we're talking about in system engineering is something called state space. State space models are a very important concept in controls in particular because they help you model not just the behavior of a specific system, but how that behavior is controlled in order to get it to do something you want it to do, to get the robot arm to go over there, to get the rocket to stay on course, to get the bridge to stabilize after the car drives over it. Right? There's many different situations under which you want to make sure the response of the system you're designing behaves in a very specific way, the way you want it to, in a way that's controlled and stays within your requirements and achieves the desired objectives. But this also goes into a lot of other different and interesting concepts as we'll see in a moment. So let's draw a few blocks here. This first block is going to be what's traditionally called the plant. Sometimes you could also call this the universe because this is basically everything outside of your control system. The term plant in this case comes from, for example, industrial engineering, where you have like a process in a manufacturing plant. You have some sort of process you need to observe and control. And in particular, let's start with figuring out what's going on. So there's some subset of information that you can perceive put yourself in the mindset of the controller, that you can perceive about this plant. Let's say this is everything else in the universe. There's some subset of measurements about those things in the universe that you care about that you're going to try and measure. And you're going to measure those things with specific systems called sensors. Okay, so those sensors are systems of their own. They have their own sort of transforms or their own behaviors. And from those sensors, you're going to get specific information about how you may want to control the behavior of the system you're interested in. So the information from those sensors goes into a controller. This could be a digital controller or an analog controller. And this may be combined with some knowledge about a desired state, right? The robot arm is here, but I want it to be here, just as an example. There are many different kinds of controllers and controller models. A lot of controller models, for example, will look at the difference between the actual and the desired state, keeping in mind that this set of states that we're interested in may not actually be, sometimes this is called X or U. Sorry. Let's erase this. You may not directly be observing the states that you're interested in, right? So this is actually a very important concept to this state space representation. What you're actually looking at are the outputs, not the state that you're trying to control. So let's say quantitatively this is a set of numbers, right? So you see some sort of output as a result of sensing the state of the system. And usually there's some sort of inversion process here where you invert this process to try and figure out or approximate what the underlying state is. Based off of the difference between that state and the desired state, you will have some sort of a command. And those commands go to the next set of systems, which are called actuators. So let's here. So the controller issues commands to the actuators, and the actuators have some mechanism by which the state of, or there's some mechanism by which they can influence the input to the system. So some of these things you'll see represented in different places in different ways. X, U, and Y are sort of common nomenclature. In particular, one thing you'll see very often is sort of this this form here. This is not true for linear systems, or nonlinear systems. Sorry. But this is a very common way to represent the overall behavior of this system. So there is some fundamental state of the system, and it changes over time. That change is defined by a linear combination of the state and the input. And then there is some output that you observe, which is, again, a different linear combination of the state and the input. So if we assume, for example, that these are constant, a nonlinear system, these are functions. If we assume these are matrices, linear system, and constant matrices, that's a linear time invariant is one assumption you'll hear a lot in systems engineering. Then we can apply a lot of powerful mathematics to this tool. Mathematical tools to this model, and in particular come up with ways to come up with like what the ideal input signal is to realize a specific state or to achieve a specific output. But even just if we put the math aside, this is a really interesting and very powerful model here. Another thing I'll point out is sometimes there's other inputs to the signal we may not control or into the state. Things like noise or environmental inputs, or just other changes as you're driving over the road, right? The height of the road may change over time. And then not all, we don't necessarily have control over every state in our plant, right? Sometimes we only have certain authority to influence through our actuators a certain subset of that state. So there's different spaces or dimensions associated with each point in this graph. But for the most part, we can think about sort of this 4-block cycle. In particular, let's put the human brain here, right? This is a really interesting phenomenon. So if you're familiar with Immanuel Kant, he had this realization or critique of rationality where he pointed out that how can we ever know it's true because we perceive everything through our own senses, right? Well, as it turns out, the state space model takes care of that problem, because what we perceive is perceived through a set of sensors like our eyes, right? And so if we have sufficient understanding of those sensors, we can account for their behavior, right? We can correct for their behavior and determine what the underlying state is, and then actuate against that state to move my arm over here or to So this idea of a system from which we can sense things, make some sort of decision about in a controller or a control model that then performs an actuation that has some sort of influence on the state of the plant or the universe is incredibly powerful. So this is state space representation. And even if you leave the math alone, this is a really interesting way just to think about the world and to think about the different behaviors and the way that different things take place. Okay, so that's That's the second. That's the first model that we're going to consider. The second model is something called I'm going to call it an optimal control model. This is more of like a time process model. In particular, I'm going to illustrate it in a very, very simple way. I used to have a song that I sang to my kids when they were very, very young with the toy taxi. When you want to go from point A to point B, you take a taxi. So let's pretend you want to go from point A to point B, right? You need some sort of a path. So this is a space, right? An n-dimensional space. It doesn't matter how many dimensions there are. And over time, at time t0, you are at time A, and at some point in the future, you want to be at time B, right? So, why is this important or interesting? Because there is a cost associated with this transition, right? So if you know point A and if you know point B, that's not enough, because you need to understand the system that's governing the movement and your control over it. Remember our state space representation, right? What sort of actuation you can control to transition through this space. And usually what that comes down to is some sort of cost function. And usually that cost is a function of your state and maybe a few other inputs, right? So over this path in time or in space, you may integrate this cost function and to come up with some sort of net cost of, let's say I want to go along that path, and let's just assume for the moment that this is a boundary value problem where we know how we know our boundary conditions, and we just have a variety of choices to make about what path to take, right? So we integrate the cost along that path. We come up with some metric. Let's say it's dollars, and we want to minimize that value. We can apply all sorts of calculus to this, and there's many incredibly powerful tools specifically to address this concept of cost minimization, because at the end of the day, cost, that's what all optimization is. Cost is an abstract arbitrary function. Hopefully it's a scalar. If it's not, you have a multi-objective optimization problem, and practically all interesting problems are multiple objective optimization problems. You need to reduce some way to be able to perform calculus against it. So why is this a particularly interesting and powerful model? Well, first, all of controls is based off of some sort of transition of control to like desired state, right? And we talked about that in the previous slide. But also, this is generically true across spaces of infinite dimensions, right? Even if point A is constrained by some subset of those dimensions and point B is constrained by some subset of those dimensions, usually B has more constraints than A, by the way. You may not choose where you start, but you know where you want to finish, right? There's three specific choices you need to make, or three specific things you need to understand. First, you need to understand where you are in the state space. So in the state space representation, this is sensing, right? But you may also need to understand how you got there. Next, you need to understand where you want to go. And then finally, you need to understand how to move through this space, how to control your movement through this space, and what sort of costs are associated with movement through that space. Let's go completely qualitative example here and think about policy, right? We know the laws for area as such right now, like the condition of the society or culture or state or government are this, and we would like to see some sort of outcome, right? There's some sort of desired outcome. If we put in place laws X, Y, Z, we think we will take this path or this path or this path, etc. Right? Based on our understanding of what behaviors exist within this system, maybe it's an economic system, maybe something else. We need to understand all of those things in order to try and figure out and take the best possible action or action to get to the desired state. This is particularly interesting for policy because no one cares about anything but B, right? Everybody always wants to talk about where they want to go, This is always some, beautiful utopian vision. No one wants to talk about where they are, how they got there, and even fewer people actually understand the mechanics of the system or the economy or whatever it is you're trying to govern well enough to be able to predict how to move to state B, and also what the cost of that transition will be, right, of moving along that way with that mechanism. So this is a concept from optimal control that's another one that's incredibly useful in systems engineering, incredibly relevant to a lot of quantitative and qualitative situations. So next, I'm going to talk about something that's a little bit closer to computer science, but is still incredibly useful when you're talking about sort of abstract transforms. Let's say you write a computer program and you want to call it from the command line. I can probably come up with some example here, right? You can tell I haven't quite mastered all of my emotions here. This is an incredibly basic C++ program, of course, but it actually ends up illustrating a couple of different things I want to talk about. Okay, so do we have? Okay, so what we have here combines a couple of different and interesting concepts. When we call this program, there are several things that take place. First, in this case, we have no inputs into this program, but we could theoretically pipe inputs into the program from some other program or from some resource like contents of a file, etc. We do have outputs that are being printed to what's called a standard output stream. And then if you look at the source, we also have different ways of determining how this program behaves by way of arguments. We don't actually process any arguments here, but they could be passed. That's sort of part of the standard entry point signature. And we have some dependencies. So in this case, we are including the library that lets us print things to the standard output stream. These concepts of standard streams are actually universal to all computer programs, but they're also very good ways to characterize a given transform in a particular process. So let's take some sort of function that performs some sort of transform, right? We have input to that transform. In this case, we're going to call this the standard input, just borrowing from the standard stream nomenclature. And because it's a transform, right, it's a function that transforms input into output. Notice we're not making a lot of assumptions, right, about exactly what this looks like. This could be anything. Given a particular program or a particular transform, or a particular function, there may actually be different ways you can configure that program or transform to take place. Let's say this is something that takes in, I don't know, a table of numbers in CSV, right? And it prints out the statistics for those numbers. Well, maybe at first it just prints them out line by line, and you want an option to be able to print them out in like a JSON format or something else, right? A Word document. The transform changes even though the underlying logic within the program is largely the same. So there will be some sort of configuration option that you may want to pass to the transform. This is like the knob on the machine, right? The machine doesn't change, but there are different ways to adjust the way that the transform is taking place. And then lastly, sort of from the bottom up, what we have are, we're going to call these dependencies. And these are out beyond the scope of that transform. There may be other transforms that cursively it decomposes into or uses, right, or imports. So we saw including IOStream, for example, in that program, right? But very rarely does any sort of transform exist on its own. There may be many other things that go into composing that transform or recursively expanding behaviors. But this standard process model is incredibly useful to characterize transforms or any process by identifying specifically what the inputs are, what the outputs are, And this, by the way, comes along with a data-oriented design pattern where you have very explicit and specific knowledge of inputs and outputs before you go about characterizing the transform itself, right? That's a good engineering practice. Some sort of configuration by which you customize or adjust the means by which the transform is taking place. And then that transform itself is comprised or defined by various dependencies that go into characterizing its behavior or implementing its behavior. There is, you may notice, one slight variation here in standard computer science, which is there's another standard stream called standard error. And there's interesting and different contentious debates about how errors are appropriately handled by any sort of transform or functional process. But let's say for a moment that you do need some sort of channel. This is not always error. Sometimes this is just log messages. But this is like meta output, right? Log messages or alerts or warnings, there's a whole syslog variation of what kind of information you want to be able to report to standard error. But this is one variation on this process. Fundamentally, a transform represents a function represents a transform between input and output, characterized by configuration, comprised of dependencies with possibly some other sort of meta output to monitor the process. And that's true for like a stop or a station on a factory line or a factory floor, for example, right? It's not just computer programs. It's true for cognitive processes. It's true for the web page that you're loading. It's true for many different sorts of just handling of information, like processes that handle information can be characterized using this model very effectively. So that's the standard stream model, and that's the third of our fourth. The fourth one is what's called the systems engineering V model, and you'll hear this come up with a lot when it comes to creative activities, specifically in systems engineering, but it's universally applicable to any sort of human endeavor. It's very interesting. Let's take a software approach first and say that you have some sort of design, right? You are working on a bridge, and the architect comes to you with the drawings from the customer and says, we like this style of bridge. Here is the design. So the design is effectively the input to the engineering process by which, and then internally, now that you have the inputs from stakeholders and other sources, there is some sort of development process that takes place by which the output is some sort of product, right, is the result of engineering that is then deployed or delivered back to the external stakeholders. This is a very simple, 1, 2, 3 step design, development, delivery process model. You can tell it's in the shape of a V. This is like internal activities, external activities, right? This is like the simplest possible model. There are many more sophisticated variations of this. If you look at, oh man, you know what I should do? I didn't plan this actually, but this would be crazy. Let's look at let's see, where's the work of art? Here we go. Oh, that's glorious. That's beautiful. So you want to see how complicated this process can get? Here is the Integrated Defense Acquisition Technology and Logistics Lifecycle Management System, part of something called JSIDS. This is how operational systems are designed or engineered and procured by the government, the Department of Defense. So what you see in here are many systems engineering Vs. There is some sort of decomposition of the design into study or analysis that is then integrated into the generation of some final product. And this takes place on many different levels, right? So there in the initial, what do they call this, material solution analysis phase, the problem is analyzed, and then there's some sort of development of technology that, again, that goes through a systems engineering V process here. There is some sort of engineering and manufacturing phase. This is largely iterative, of course, because you don't come out with the final product the moment you start building something. But eventually you get to initial operating capability, then you start full-scale production, eventually reach what's called FOC, or final operational capability. And all of these things involve, right, here's your prototypes, here's your full rate production, different Vs. Every single process in that system engineering effort is characterized by some variation of that sophisticated V. But it's the same pattern at the end of the day. There are some sort of design requirements, objectives, inputs from stakeholders that are established at the externally, that go into an engineering effort that develops a solution based off of that design, and then that solution is then delivered to either the next step or back to the stakeholders or some external party. This is also relevant, incredibly relevant to software engineering. If you look at any sort of issue model in GitLab, in GitHub, in Redmine, in Scrum, in anything else, there is some variation on this that characterizes, for example, the life cycle of issues, right? Like Bugzilla is a good one. Life cycle. This is going to look like more of sort of like a state transition model. Sure, none of these diagrams are very good. I should have pulled this up. Sure, let's use this one. It's not the best one, but it works. Same thing. Doesn't look like it, but you have effectively some sort of request that is generated with inputs from external stakeholders. It is assigned to an internal process by which it's resolved, right? The engineering improves or is performed to generate a new product or improve the product, and then it is released. It's verified, it's delivered, and subject to confirmation or approval or review, right? So this V model is incredibly relevant and just shows up all the time in any sort of creative endeavor. Let's say you're a sculptor, right? If you're an artist and you don't care about engineering, and someone says, hey, I need a new statue for my garden. Well, they're not going to just accept anything. They're going to say, well, it needs to fit in this space, right? It needs to fit well with the aesthetic of my garden. There are going to be inputs and constraints and requirements, or a drawing of a character. This character needs to have da da da. I'm going to sketch this cartoon of this person who has to leave these characters. There's some sort of design that takes place that goes into the development of that artistic product or aesthetic product or what have you, that's then delivered back to, there's probably steps here. There's iterations that take place. There may be different drafts, different cycles for feedback to iterate on the design. But at the end of the day, there's still some sort of V-shaped engineering process. Design, development, delivery process that's taking place. So let's take a quick moment to sort of review and summarize. First, let's go back to the state space representation, right? We have some sort of plant we're trying to control. There are some sort of sensors that are giving us information about that plant. The controller makes decisions about what needs to be done to achieve a particular desired state. Those decisions result in commands to actuators that affect the state of the universe or the plant in some way. Next, we had the optimal control model. This is given some sort of desired state A, or some sort of current state A and some sort of desired state B. There is some transition by which you can go from A to B. So some sort of path that has some sort of cost with it, and maybe you want to minimize that cost. You need to solve for the path of transition that minimizes that cost. Next, we talked about the standard stream model. So this is a model of transform processes that those transforms take an input and they turn it into output. There's some sort of configuration that defines this, basically the state of that transform, the specific behavior of the transform. There's some sort of dependencies that go into the implementation of that transform, and then optionally there may be some sort of meta output for errors or warnings or logs. And then lastly, of course, we talked about the systems engineering V model. At its most basic form, this is a design, development, and delivery a model by which pretty engineering or any other creative endeavor takes place, where inputs, design is given from external stakeholders. There's development that takes place to create something, and that creation is then delivered, maybe supported or sustained or subject to approval or some sort of iteration. So these four models are absolutely fundamental to systems engineering in particular. And you can see possibly, especially when I start talking about state space, right? The space here, there's control sensing space, there's actuation space as subsets of those. Um, and that's space by which we move through these things. That transform for each of those processes may be characterized via some stream model, and then the development of those things may take place through. These are all related, right? But they're all very interesting, very useful models that aren't just quantitative. They can actually be very useful for everyday life as well. And you'll see, once you sort of grok them, you'll see them pop up everywhere in life and everywhere someone's talking about a problem. That's it for today. Next week, I think I mentioned we're going to start the next fundamental engineering segment. Given I'm trying to do 52 of these, and this is like, what, 13? And that's assuming I never get around to finishing or figuring out the VM image one that I mentioned last week. We'll probably be stepping it up to 2 a day here pretty soon. I think I have to. I don't think I have a choice. But fortunately, since we have a more specific a line of efforts, if I don't want to go off and do random other things like commentary on game engines, which is entirely possible. We might do like one engineering one a week and one non other like software or some other commentary thing a week. But for now, you can assume that like the fundamental stuff will probably be sticking around. Take care.